In this video, we're going to talk about catalysts. So a catalyst is something that increases the rate of the reaction, but is not consumed in the reaction. So oftentimes, or all the time, a catalyst will be used in one step, but then we regenerate it in a later step. An example of this is shown down here at the bottom, where we have iodine with a negative charge on it that is used in our first step here in our rate determining step. But then in the second step, we get iodine with a negative charge back. So we regenerate this iodine, but it doesn't show up in the overall reaction because we use it in one step and then produce it in the next step. So if we add these two reactions together, it would not show up in the overall reaction, and it doesn't participate in the reaction. It just aids in the reaction happening to speed up the slow step. So a lot of times, because the catalyst is involved in the rate determining step, it ends up showing up in the rate law. So we would write our rate law based on the first reaction, since this is the slow step, the rate determining step. So we would have the rate is equal to H2O2 times iodine to the -1. So here's another example, or actually this is the same example. We have our peroxide in a flask down here. H2O2 will break down into oxygen gas and hydrogen gas over time, but it's a rather slow process. If we want to speed that up, we can use something that contains iodine, something like sodium iodide, which in this case is in aqueous form, and that will speed up the production of O2. So we can see, without any catalyst, our balloon is rather flat and doesn't have any O2 in it. When we add the catalyst, this reaction gets much faster and we start producing some oxygen gas here. So if we think about this in terms of a reaction coordinate here, and we think about this graphically, if we do this uncatalyzed, which is the graph on the right here, we have to go from reactants to products, but this is the hump that we have to get over. That's a pretty large hump, so not very many of your reactants are going to make it over that hump. So we're not going to get much in terms of products. If we do this the catalyzed pathway, we now have two smaller humps to get over. The first one is a little bit higher because this is the rate determining step, but it's still lower than our activation energy was for an uncatalyzed pathway. So we will get more of the reactants making it over this hump to get to the products. So we can have catalysts that are in a different state than our reactants, and we can have catalysts that are in the same state. If a catalyst is in the same state as its reactants, we call that a homogeneous catalyst. So it's homogeneous, it's in the same state, whether those are solid, liquid, or gas, it's in the same state as the reactants. A heterogeneous catalyst is something that's in a different phase than the reactants are. So an example of a heterogeneous catalyst, if we have something like H2 and C2H4, which are both in the gaseous phase, and then we have our metal catalyst down here, the hydrogen and the C2H4 get absorbed onto that metal surface, causing those hydrogen bonds to break. And then once we break those hydrogen bonds, then that can react with the C2H4, and we eventually get C2H6 as our product. So our reactants are in the gaseous state. Our catalyst is a metal surface that's in the solid state. So this would be an example of a heterogeneous catalyst. So this table here gives you some more examples of catalysts and what they're used for. So things like forming ammonia, which is used for things like fertilizing and farming. We've got some down here with different metals as our catalyst. So those would be heterogeneous catalysts usually. So these are some practical examples of where we use catalysts and things that we need in everyday life. So we're actually going to wrap up here, and we will talk a little bit more about catalysts and get some more practice with all of these reactions in class. So I will see you in class.